Okay, so let's just talk the experiment that were involved with the game that you played since the last class and what you just played. Okay, so the first game, remember that you played the push and pull game, but that's basically the prisoner's dilemma. Okay, and although you play the version that you repeated play with the same person, but based on the theoretical prediction that we talked about in the last class, that's the same as the one round prisoner's dilemma, right? So in this paper, Cooper et al., 1996. Oh, by the way, the paper I cited today, which also have the reference list at the end of the slide, which you can already download on the EE class. You can also choose a paper among those. Okay, if you still haven't chosen your presentation paper. So the first one, in the 1960s, David Cooper and a bunch of scholars, they researched out they basically run a series of experiments using the prisoner's dilemma. What they do is also a repeated game setting, but they use a matching mechanism called stranger match. What is a stranger match? Basically, that means you are repeatedly matching with a new participant in this room or in the lab, but you never meet the same person twice. So, for example, if we're running that protocol here, because we only have 10 people, so if I let you meet with another person, so we can at most have C10 choose 2, that many matches. So that's actually 45 different, 45 different matches. That's the most we can get. Okay, so that means we are limited to how many rounds we can actually round, basically. So when you use a stranger match, that's as if you are running a lot of one-shot prisoner's dilemma. Understand what I'm saying? You're running a lot of one-shot instead of a repeated game. Because you're meeting with someone new, you cannot have a history with this guy. You cannot make a promise that I will make up to you in the next round, for example.
It will still be to church from the one we had before.
You never match, that's what it means, stranger match. When you say stranger, you never met with someone you already met.
Yeah, but if for example, the first couple of times I wanted to cooperate, people didn't want to, so I've been, I lost. And so afterwards, even though it's someone new and a stranger match, I won't cooperate again.
Why do you want to do that?
Well, because like all the time I tried to cooperate.
But all the time you try to cooperate, the other person doesn't know.
That will be very different from
You only observe your payoff. You and your opponent's payoff after you play. But that's so in T equals 1, the first round, you play with Ben maybe, and then you both choose something, you observe what the other person choose and what's your payoff, and then you will match with next round maybe Ines, and then you cannot see Ben's payoff in this round, for example. You only see your payoffs and Ines' payoff in this round. So you have no incentive to cooperate in the sense, or if you don't want to cooperate in one round shot, theoretically you don't want to cooperate even if you've played many, many times. That's theoretically at least. Yeah. So, but what they found in the experiment is actually that in early round, the cooperation rate is 43%. In early round, there's a lot of cooperation. But it's true that in later round, they actually only play 20 rounds. Okay, so in round 15 to 20, the last 5 rounds, This is also called the endgame effect. So usually in the early round, people are playing as if they play infinitely many rounds. So they have some sort of cooperation. But in the last few rounds, people would notice that we're almost end. There's no incentive to cooperate. But it's still as high as 20%. Remember, what's the theoretical prediction of this percentage? What's the theoretical prediction? It's 0. Because the theoretical prediction that people will always confess. So there's 0 cooperation. So the theoretical prediction is 0%, but that's not true. Okay. And to explain this, there's actually more than one way. Okay, so and because PD is like one of the most famous games, there's like a whole bunch of paper talking about this. But basically, the central idea is called the so the easiest explanation would be a taste for cooperation. Basically means people have an intrinsic value on cooperation. Or sometimes people say this is called so-called other regarding preference. So traditionally, economists assume that you only care about your own payoff. So that means when I see this table, I don't even need to see the -3, -10, -2. This number are sort of irrelevant to me, in a sense. In a more general game, this is actually not true, but because you need to know what's the other person's strategy, right? But in this specific game, because this is a dominant strategy to confess, right? So I don't even care what the other person's choosing. I simply want to choose confess. That's the end of the story. But what's other regarding preference? That means, for example, if we end up here, although I am so happy I only got 1 year sentence, and the other person got 10-year sentence. Theoretically, I shouldn't care about him. But if my utility function looks like this is the opponent's payoff. This is my payoff. For example, this means I care about my payoff, but plus the alpha here. Okay, so I care about my payoff, which is x, but I also care about what's the difference between my payoff and the other person's payoff. If the difference is too big, the alpha is negative. Okay, if the difference is too big, it will actually makes me unhappy. This can be separated into two effects. One is called envy. One is called guilt. Envy means I have more than you do. I have less than you do. So I'm envy of you. In this case, the difference would also be big. What I get and you get would be big, right? And the other one is guilt. Is this case. So I only get 1 year, but you get 10 years. I'm guilty. I feel guilty. Okay? So this one also make the difference big. If you have this kind of utility function, which is non-standard utility function, you can explain a lot of these effects. Why people cooperate, basically. Okay. I don't have time. I don't think I will have time to show your data today, but I'll definitely show your data next week. Okay. And the second experiment we play is the matching pennies experiment. This one in the 01 paper, they basically played this game, but instead of a 1 minus 1, they use, I think, 4 1, 4 1, 1 4, 1 4, something like that. This is because actually in this game they also didn't use a minus number, a negative number. Because in the experiment you don't want to take money from the participant or subject. But basically if you think of, you change the number to 4 1, 1 4, 1 4, 4 1, this is exactly the same game. The theoretical prediction is also the same. Remember the theoretical, we talked about this last week, okay, so yes.
There is it's not really the same thing because people will act differently if they know they cannot do the same thing. Like, whatever it happens, if I won 4 or 1, whatever it happens, I will win something. They can't use, it's not minus 1 like people
I don't understand what you're saying. We can talk about that later if you still... what I'm saying is, if you run the analysis that we did for this game, that we did last week, you'll find that the theoretical prediction is still that the Nash equilibrium is you play half head plus half tails. Both of them playing this strategy will be the Nash equilibrium. Okay? And in this case, we also played it repeatedly and with a stranger match. And this one, the theory did a pretty good job. Basically, subject do play heads and tail with equal probability. Okay, so it's actually not hard to find out that you should randomly fit. Okay. And the third one we played, I didn't specify it, but you were actually playing the bed of sex experiment. If it is not, if it's not clear. With the numbers also a little bit different, but it's exact. The spirits is the same. Okay, and remember the prediction is that there could be one equilibrium like this, one equilibrium here, and one mixed equilibrium. So in this case, we use a repeated. In one experiment, they use a repeated, but this case pair match. Pair match is what you just did. You pair with the same person along the whole experiment. Okay? And what happened is, because I don't want to stick to, for example, this experiment. If this equilibrium, if I am player B, right? Because I always get 1, which is less than 2. But the wife or the player A doesn't want to stick at this equilibrium as well. So they basically take turn. Half of the time they stick with, they do ballet. Half of the time they, one round ballet, 1 round boxing, and they realize, although they cannot chat with each other, but they figure out this like a cooperation strategy. Okay. And what they also do is another experiment where this time is a stranger match. Remember, stranger match, although we repeated it, it's just as if it's a one-shot game. We play many one-shot games. The reason why we do this is because we don't want actually one-shot game, because in that case we only observe one data point. For a study or research, we want many data points to conclude on the result. Okay? Just in case you don't understand why people use this kind of match in the protocol. And what's interesting is that in 5 rounds, remember that the Nash equilibrium we were trying to find in the last week, it was not that easy to find, right? We used a few lines of math and to derive that. And you might not even understand how to derive that right now. You might need to still go back to review that. But in 5 rounds, if you actually play this game, people's strategy converge to the Nash equilibrium, the mixed Nash equilibrium. Sorry, I forgot to. Converge to the mixed one, the mixed Nash equilibrium. So it's pretty amazing. And wait. think it's right. Okay, so the next game you play, the investor and responder one, that game is also called a trust game. Okay, so the truster or the investor, he or she this one is a simpler version where the investor can only choose to invest or not to invest, and the trustee can only choose to betray or share the money. But the idea is the same. You can get it, right? So they play this one shot, and when they play this one shot, the payoff actually matters a lot. What I mean by payoff is, so if between betray and not betray, as a responder, if betray only gives me a little bit more, not too much, although it's still more, okay? If I betray, I only get, for example, $2 more, and I can heavily damage the investor. Versus the other case where if I betray, I will get a lot more and also heavily damage the investor. In terms of the SPE prediction, these two cases are the same, because the responder should take more when he can. Oh, by the way, I forgot to say. So what's the prediction? What's the theoretical prediction of this game? Remember, we go from the bottom, right? In the bottom, the trustee wants to betray, because if he betray, he got 40 instead of 20. And if the investor, the truster knows that the trustee gonna betray, instead of 0, he wants 10, right? So he will not invest. And in the version you play, what's the theoretical prediction? You can choose any number, any amount of money you invest. Again, backward deduction. You think about the responder first. No matter how much money the investor invests, what's the best response for the responder? Return how much? 0, yeah. And given that you know as the investor that the responder are gonna return 0, how much would you invest? Also 0. So that's the theoretical prediction. Just like this one I wrote here.
But after many rounds, the game.
Again, if you repeat finitely many times, it doesn't change the prediction. Just like the PD, because you go to the last round. The last round, the responder will want to do the same thing. He wants to betray, right? And if the last round the responder wants to betray, as the investor, you don't want to invest money. And if you already know the last round is going to look like that, in the T-1 round, you also want to betray and so on. Yeah. But unlike the theoretical prediction, the payoff actually matters a lot. So if the responder, if by betrayal, he only increased his own payoff by a little bit, but heavily damaged the other person, this person would tend not to betray, although betray is still in his own benefit. Okay? So, but which is not what the SPE predicts. And in general, basically, a lot of people still invest, and a lot of people still return. It's also what not the SPE predicts. And the pumpkin game you play is also called a centipede game, because the game tree, this is the game tree, looks like a centipede. Okay, in a way. Okay. So this S is basically the pumpkin size. The pumpkin size will double each time in this specific version, okay. The pumpkin pie double each time you push, you pass, but you also, this is the first person, this is the second person. So if the first person take it right away, he got 4, the other person got 1. If we push and the other person take, then the first person get 2, but the second person get 8. If the person further push, pass, then now if the person take, so this is pass, this is take. Is that clear? Okay, and so on. So if both person just pass to the end, they actually can both get a lot of money. For example, 54 and 26. Actually, some game we can, in some version of experiment, this can go even further. And if both people cooperate at the end of the experiment, they can both earn up to few thousand US dollar in the lab. Yes.
Why does the ratio change? Okay, the beginning the ratio is 1 to 4, and like at 1, 1, 2, 3, 4, 5, it's like 1 to 2.
The number doesn't really matter here.
Well,
It doesn't really matter. That the prediction doesn't change. Yeah. Okay. So the key here is that if you pass, you are risky at the other person not pass, but take. That's the key, right? So, what's the theoretical prediction? What will happen? What's the theory prediction?
Well, pass until the trigger.
The theoretical prediction, again, we use a backward induction. Okay? So if the last decision not, what would the second person do? The second player do? Not pass, right?
So theoretical is never pass.
Yes. Theoretical prediction is you never pass. Whenever you have the chance, you take. Okay. But if you also do this with a stranger match, repeated, actually only 8% of the player 1 stop immediately. That means, player 1 will take the pumpkin immediately. Most of the game actually ended in second or even third round. Okay. But it's also true that you can never go to the end of the game. It just, nobody will risk that much. Okay. And the repeated prisoners dilemma experiment. So this version is the version that you play next, which you have some probability of continuation of this game. So the theoretical prediction, I already talked about this in the previous class. Basically, the prediction is that if the grim trigger strategy is possible, then cooperation should be able to sustain. But what happened? It is true that between two different conditions, in one condition the grim trigger can sustain, the other one the grim trigger cannot sustain. It is true that the cooperation rate is much higher when the grim trigger is possible. But the theoretical prediction only makes the difference of whether so the theoretical prediction is like this. So this is grim trigger. So if grim trigger is possible, the probability P or G is high enough, then the prediction is yes, we will have cooperation. And if it is low, the probability is low, then the prediction is that is too low, then the prediction is no, we won't have any cooperation. But what happened in real life is that, in the real lab experiment, is that it's not really yes, but just higher. And this is not no, but just lower. And also, the higher the probability, the higher the cooperation. So is sensitive to both the continuation probability and the cooperative payoff. How much more you will get as a cooperative action. Okay, so this is also what not the theory predict. The theory makes a clear-cut prediction. It's whether there's yes cooperation, no, there's no cooperation, either way. Okay? And the last two games, sorry, a little bit late, but I want to finish this so that we can talk about the presentation next week. Then this game is actually run by this Alvin Ross is actually one of the Nobel Prize in economics a few years ago. So the next game is the ultimatum game that you play. Basically, the sharing proposal of the pie game. You instead of 10, you share 100, and then the second person decide whether they accept the offer or decline the offer. Okay, what's the theoretical prediction? So what would the second person do? Accept or decline? Accept, yes. Because x is greater than 0, so x is greater than, so x is greater than 0. If the first person knows this, basically the second person would accept as long as this x is greater than 0. What would he do? What would he propose? Only a few. So basically, if in this case it only gives like 1 cent out of $10. Basically, it's just like 1 point out of 100 of your case. So the theoretical prediction is that the first person will propose 1, and the second person will take the 1, not decline it. Okay. But I don't know what happened in the game that you played, but I bet that's not what happened. Okay? So, in fact, they run this experiment, actually, this is a very famous study, actually. They run across a lot of different countries, not just modern society, also like this kind of developing country, or even like a traditional bush economy that's kind of, inside the deep mountain, that kind of area. Okay, in Indonesia, in I think also in India, in some really, really remote countryside.
Monkey also.
What's that?
The monkeys also perform this experiment.
Sorry, what?
They also perform the experiment with monkey.
Yeah. They also do this with monkey. That's true. This is a very popular experiment, so they do this a lot. But the key here I want to talk about is the human one. Okay, so in modern society, people usually propose something around 4 to 5, just half or 40%. And the unfair offer are rejected most of the time. By unfair, I mean not 50-50 or not close enough to 50-50. Okay, in the bush, so in like traditional society, interesting enough, that's actually highly depends on culture. I remember one case really stunning to me when I was a student. I heard these studies that they run this experiment, I think, in one village in Philippines. What happened is the proposer actually proposed something like 1 to himself and 9 to the other. So he proposed more to the other, but the other person would decline that offer. Okay, because in their culture, this move of making an offer of 1-9, making 9 to you, that's a gift. And in their culture, you don't accept a gift like this because it comes from nowhere. Okay, and what they also find in this study is also, I think, is very interesting, is that they find that maybe a little bit opposite to your, counter to your intuition. A more market economy or more capitalism economy, basically, has more fair offers. Okay, and my explanation or the paper's explanation to that is because in a market economy, no matter you like it or not, you have to make a lot of the fair trade, in a sense. Because if your offer is always very unfair, you will be disliked by a lot of people, and nobody would like to make trade with you in the future. So you tend to taking this kind of value of fair into your mind. Also, I didn't write it here, but do you think baby tend to be closer to the natural equilibrium prediction, basically propose nothing and accept everything, or they actually make fair offer? Which one? Yes.
It depends because, for example, in France, when you have a lot of babies, you can have a suggestion from the state to help you with the money, so the baby makes you learn some money.
I'm talking about baby who cannot even understand the government policy. It's like few months old. The baby as the proposer, what would it actually, or little children?
Will it be closer to the theoretical?
Yes, they were actually close to the theoretical prediction. Because this kind of fair idea is actually quite sort of socially told, not our intuition or not our born gift, sort of. But that's not always true, obviously. But generally speaking, that's true. And the really last game we play basically is the automatic game without this reject or accept, right? That's called a dictator game because the first person is just like a dictator. It dictates whatever you propose. Obviously, the theoretical prediction here is even clearer, right? The first person should just propose nothing, right? There's no incentive for him to propose anything. But actually, only 18% of the proposer actually passed 0. About a third of the people actually passed 4 or more. 40% or more. And they thought that this is because this is not a double-blind experiment. Because that the experimenter is observing you, right? So you want to show that you're not that selfish asshole. But so they do this in a double-blind version where basically the subject nobody can know how much they propose, and they basically put their money into an envelope, and the envelope was scrambled and then displayed to the next, and the experimenter really cannot identify who proposed what, but they still know the whole statistics, right? And even when they do that, it's true that now fewer people propose, more than 4. But so basically 2/3 now pass 0, and fewer than 10% now pass $4 or more. But remember, the theoretical prediction is nobody will propose anything. So even that 10% of the people propose $4 or more is, not explained by traditional theory. It's a very behavioral thing. Okay. But what interesting enough is that, also very interesting, I find in another study, is that if you let the dictator work on something, like work on a puzzle, solve a puzzle or solve a quiz, and sort of tell him that after this quiz or puzzle, you earn this money. And then this dictator divide this money with another person. Because you create this idea that this money is his money, then this person really won't give money to the responder. He will keep everything. He will basically pass 0. But this is still only true with double blind. If you still don't use double blind, people think that you don't want to be the asshole, basically. Yeah. Okay, so that's it. Thank you. I will actually assign some. I will assign some homework based on the. I mean, you need some practice. I mean, otherwise, you won't be able to do the dictator well. So I will assign those question on the EE class, and the question is gonna come from the PDF reading material that I upload for the game theory part. Okay, and you also submit the homework assignment next week. And next week